Hello. So we're gonna touch on area triangulation methods today, and area triangulation is really synonymous with the triangulation that we know, in the sense that the objective is to extend control. So what do we mean by extend control? To extend control is to just take increase the number of controls within an area in such a way that you cover a larger extent, or reach places where you couldn't have reached. So in the countries, the establishment of a country, when Ghana was formed, the first thing that was necessary to do was to map its boundaries. And so triangles are formed, and then controls are placed as we go, so that you can actually compute the next coordinate, the next unknown coordinate. So that is the objective of triangulation traditionally. So aerial triangulation means that we want to also extend control, but in this case, we are looking at aerial photogrammetry. How do we, extend control? Because everything that we're doing is surveying, aerial photogrammetry is to make sure that we have, computed or obtained the XYZ coordinates of all points. Okay, all points within the photograph, on the photograph. So what do we do traditionally? What we have done with area triangulation is that we had to actually use manual processes, but obviously we can look at digital versions as well, or semi-analog versions. Are you okay? All right. So area triangulation is used extensively for many purposes. Like I said, one of the principal applications is identifying ground controls through strips or block of photos to be used. So in other words, if I can go to my whiteboard, I'll be going to a whiteboard in a minute to show you, what I really mean by identifying the controls using photographs. Going to my whiteboard. I hope I'm able to, let me clean it. Let me clear it up. Excuse me. So we have photos. We start with one photo, then you can add another one. Okay, and then you can add another. Okay, I think my marker is messing up as usual. All right, so you can add a third one. So now you're having a strip of photos. Okay, and you can add another, and so on and so forth. So this is a strip that you can turn around and keep going. But as you move in this direction, as you join photos, as you form strips of photos, okay, so you have single photo. Talking about densification of controls from a photogrammetry point of view, you can have a strip of photos, and you can have a block of photos. Okay, so in that case, then we've turned around, and then you are coming back. Okay, so we have this kind of situation. In fact, I'm not using my hand to draw, so it's not looking very nice, but that is the idea. Okay, so now you have a block of photos. So everything that we are seeing here is really a block of photos. Okay, so the strip, so there are two strips, and then there's one block of photos. Let me just say 6, made up of say 6 photographs or 8 photographs. Are you okay? So 1, 2, 3, 4. Then you do 1, 2, 3, 4. At the bottom, then you have a block of photos. So that is Ariel triangulation for you. The idea is that I should be able to establish or determine prior to flying on the ground some controls that can be also that we can capture onto the photograph. Are you okay? And then if I get those controls, I can extend the control. And I can extend the control because remember we've learned absolute orientation, and absolute orientation make sure that we can level the model and scale the model. Once you're scaling the model, then obviously we need the controls to do that. So a model that has been scaled can be measured. Okay, so a map without a scale cannot be measured. You wouldn't know what you are measuring. You'll be looking at some routes, but you wouldn't know which scale rule to use. You wouldn't know how to measure. Okay, so that's the wisdom behind area of photogrammetry, that because we can do IO, interior orientation, can do relative orientation, and we can do absolute orientation. We also, at this stage where we do the scaling, okay, we can now make use of the photo controls, I mean ground controls if you like, and then be able to excuse me, extend the control. Okay, so the extension of the control is where the issue is. Are you okay? How do we then extend it from one block of photos to the next? Okay, because if just having 2 photos will form one model, okay, in the overlap region. So we are going to be having this the model. Okay, the model we forming the common overlap. All right, so now if we actually add a third one, then there should be a way to really determine the coordinates for all photo points, you know, in the second model. So now we have 2 models. Okay, the first model is to the left, and then the second model is actually somewhere here between photo 2 and then photo 3. Okay, so there's a first photo, there's a second one, there's a third one, and then there are 2 models. So it takes 3 models to make 2. It takes 3 photos to make 2 models. You need to be able to, as a student, that's what you need to, these are the things you need to know. Are you okay? You need to have this basic understanding before you give the wrong answers. Are you with me? By the time we've actually formed the first module, so module 1, 2. Okay, so we have module 1, 2, and then we have module 2, 3. Okay, at the time we've done that, we now have to figure out how do we move from this model to this model after carrying our relative orientation. How do we move from this model to that model so that the 2 are seamlessly joined? So that becomes the objective of Ariel triangulation. You get that? So it's like doing a survey in one area and then trying to bring it all together so that you can, you know, it's like some adjustment. So of course, that's why adjustment, bundle block adjustment becomes the next topic that we talk about. Are you okay? All right, so we have so many photographs and we will need to extend control without providing a lot of ground control, because if you're going to end up providing a lot of ground control, it will defeat the purpose of the triangulation. I don't know if you follow it, but it is going to defeat the purpose. If you have to spend a lot of money in trying to provide controls everywhere on the photograph. You have to, no, you don't do that. What you want to do is that every 2 to 3 photographs, you want to provide 1 or 2 controls, and that is it. And you need a minimum number, which is enough for you to carry out your absolute orientation. Relative orientation doesn't require controls. Absolute orientation does. Are you okay? So the reasons why you want to do aerial triangulation is what we see on the board. Okay. Some areas are not easily accessible. You should take note of that access. Okay. Sometimes field surveys are just difficult. Are you okay? And then sometimes we just want to extend the control. Okay. And so the justification for aerial triangulation. So there are a few methods that are proposed. Is okay. There are a few methods that are proposed in aerial triangulation, but let's see the justification. The problem with absolute orientation is that when we have actually finished with absolute orientation, then there's a problem that we have to do. In fact, we have to deal with. And one of the problems is that the common points between the two, the common area, the triple overlap. No, not this one, even the triple overlap. Yeah, more the triple overlap area where we have 2 models coming together. There's always going to be an issue, a disagreement. Are you okay? Between, as you can see over here, the 2 models. In fact, since it's an overlap area, we need to have the points they are agreeing. So if we separated the models, model 2, 3, and 1, 2, okay, we will be having N2 points, N2, okay, which is like N standing for like nodal point, ground nodal point, okay, because it goes directly under the exposure station O2. You realize that the 2 are not coinciding, N2 and N2 prime, where N2 belongs to model 1, 2, and N2 prime belongs to model 2, 3. The 2 are not agreeing in terms of height. Okay, and of course we are exaggerating because I'm only explaining this. The ideal situation is what you are seeing here on the right hand side. This is what we want to have, so that we have a terrain that's seamlessly joined from model to model. So in other words, it's not just model 1, 2, and 2, 3, but even going into what 3, 4, if we were to actually draw another model here. Okay, of course, I'm not drawing it well, but if I were to draw another model around this area, then the model formed, if I were to introduce a new projector here, let me put it that way, to form a 3rd model, that model should also agree that in terms of height at the common area. Okay, so that problem is what we are trying to solve with aerial triangulation. Okay, so aerial triangulation make use of a few methods. We're going to look at the classical methods that are used. Is okay. So this is from the top. Planimetrically, you have the situation on the left to be a problem, which aerial triangulation try to solve, so that we have the situation on the right hand side. In fact, the only thing we do is to scale, the model on the right. Are you okay? Once we change the separation between O2 and then O3, all right, a bit, we now have it agreeing. Are you okay? Or anything that we do to make sure that the height, okay, at point O2 and then N2 prime, N2, N2 prime agree. If these 2 agree, then we are actually heading somewhere. Are you okay? So this problem is what we are trying to solve in aerial triangulation. All right. So moving on, the first method that is proposed is the Lumbar multiplex method. Okay. Why is it called Lumbar? Because you stick the projectors on them. We've talked about what projectors are. That projectors really consist of lights, a light source, a photo holder, a lens. Are you okay? And then there should be some kind of frame to hold it together. But the whole idea is to project from a positive transparency, also known as what, a diapositive, okay, project it and then to view the model, you know, a little bit more enlarged model, which we are going to be scaling, etc. So in the lumbar multiplex method, then there are a few things that we have to do. So the first two projectors are placed at one end of the lumbar and the relative orientation. Of course, you need to, it's assumed that if you are doing area absolute orientation, area triangulation, you have done your interior orientation, corrected for it, you've done relative orientation. Are you okay? So we place the first two at one end of the lumbar, obviously. I'm looking at the left end, and then you do some relative orientation. A third projector is now introduced and placed on the lumbar at about the correct base length. Okay, so you actually doing arrow like as if you never did it. Are you okay? So you do that, then you carry on with a one projector orientation. Okay, and then you are on, or you are now ready to do the absolute orientation. Once you are done with relative orientation, is that okay? All right. So the only reason why you do a one projector orientation, relative orientation, is because you want to keep the other one fixed. Are you okay? So when you introduce the third projector, it's assumed that the first two, you don't want to touch the second projector. Okay. So yeah, I don't have a diagram for lumbar, but you can just imagine that you have that situation where you have what, 1, 2, and then 3, you know, like as we were looking at over here. Here we have these two, all right, in this diagram, and then we are introducing the third one. That's what we are saying, the lumbar. So the bar, so the bar is actually kind of going this way. That is why they are called the lumbar. And you can put a maximum of about 8 projectors on it. All right, so let's take note of that. All right, so what do you do after that? To scale the second model, we know the height reading of a point on the baseline of the first model. So in other words, the trick is to know that, okay, my first model that I've done, the height for a point which is actually common to the two models is this value. Are you okay? So we know the height reading of a point on the baseline of the first model in the vicinity of the second nadir point. Are you okay? So we are referring to N2, N2 prime. Okay. All right. So the air base of the second model is then changed. The second model is on the right of it by moving the third projector until the height reading of this point is identical in both models. If the points N2 and N2 prime have the same height, then it's assumed that the two models have actually merged and they have fitted very well. Are you okay? All right, so that's the whole idea. The common overlap now provides two checks, obviously. First, the height of the 2 points AB should now agree, showing that common omega tilt is the same in both models. And then secondly, so these points are really at the wing points. Okay, so I wish I could draw an aeroplane right now, but yes, the wing points, if you look at the wing points, the two can help you to find out the orientation of the plane about the x-axis. Therefore, the common omega is all right. So if you give an answer like this in an exam and you don't, you say common omega and you say common phi, it will be so wrong. It should be just like 0, are you with me? Because the wing, when you tilt an aeroplane, one wing goes down, the aeroplane will be rotating in about the line, the flight line, about the flight line. Okay. So yeah, secondly, the planimetric positions of the two wing points should be identical, showing that the scale and orientation of the second model are also correct. Okay. So we shouldn't only, those 2 points shouldn't only agree in height, but also planimetrically, they should be identical. Okay, because we're not only looking at the height, we also are looking at the alignment as well. Okay. So this is it. Basically, this is it. Okay, so we can keep on adding more models. Further modules may be connected up in a similar way until the end of the bar is reached. And we are seeing that usually about 8 modules can be joined in this way. Are you okay? All right. Now there's also the classical method using the Zeiss Parallelogram, which makes use of the Zeiss Parallelogram lens arrangement. Okay, so the Zeiss Parallelogram is we getting that name from a certain lens arrangement that allows the left eye and the right eye to be switched in terms of what can be seen. Are you okay? So the best way to explain this method is to look at this diagram here. So you are looking at, the left eye is looking at the left photo, the right eye is looking at the right photo. But what we can do is that when we are done with forming the first model, we do not introduce a third projector. No, using the 2 projectors, we remove the first photograph and then introduce the third photograph here. Okay, and then when we do that, we switch the lens arrangement. Are you okay? So that the left eye look at the right photograph and then the right eye look at the left photograph. Okay, if that is never possible really without the Zeiss Parallelogram lens arrangement, hence the name. Are you okay? So once that is done, then of course let's just go through like the basic steps that is done. Okay, so we start with a base in the inside position, as in, okay, so we have inside and outside, positions. With the positive in the negative plane, the common areas of the 2 photographs are placed in the outside position. So these are just ways to make sure that we have an overlap in the first instance. The first model is oriented in either absolute or convenient orientation. Photo 1 is then replaced by photo 3. This is where the magic happens. And then the common overlap now falls on the inside sections of the photograph. The viewing optics are therefore switched over so that the left eye now views the right hand photograph and vice versa. Otherwise, the operator will experience a pseudoscopic. Obviously, if you are not really looking at it, if your left eye is looking at the right photo and then your right eye is looking at the left photo, you are going to have a certain feeling, which is not good. Are you okay? Because it's not a proper overlap. Are you okay? So we switch the optics such that your left eye is looking at the right projector, which actually has the left photo, which has photo 2. Are you okay? And then photo 3 is being looked at by your right eye, which is actually on the first projector. Are you okay? So it's quite an interesting one. If you really understand the principle, you can always explain how this works. So here too, it can be repeated. The process can then be repeated by placing photograph 2 by 4. Are you okay? So now you have photo 3 and 4. In that case, you switch back the optics so that left is 3, right is 4. Like these are things to just let you think. But these are classical methods that were used, very, traditional, manual, analog methods. Are you okay? All right, so there you go. And then here, this is where we are switching the optics. Is that okay? All right, so that is the Zeiss Parallelogram, Ariel triangulation by the Zeiss Parallelogram method. We also have the use of inclinometer. These are not being used today. You just, because you're a student, that's why we bother you with these things, so that you become more like a professor of sorts. You know about a lot of things that are not necessary. Like, of course, we will be looking at the actual, how the software is used. We do the practical soon as we are done. And that's why we shouldn't be missing a lot of lectures. The more lectures you miss, what time are you going to use? Are you with me? All right, but let's carry on with the use of inclinometers. So with the use of inclinometers, the inclinometer is like some kind of spirit bubble, which has a screw attached to it, so that you can actually you know, obtain the orientation and tilt directly by reading the bubble. Okay, so we have two bubbles which are perpendicularly arranged. Okay, and so that is what we're going to talk about over here. All right, so here we make use of graduated dials. So the dial is like, you know, those markings on the spirit bubble, so that we're able to measure common omega and common phi. Obviously, when you look at this one, then this one is going to be common. If the fly direction is to the right, this one will measure common phi. Okay, so now as an assignment, which I'm not even going to collect, you have to try it for yourself. Just convince yourself that what I've put on the board is correct. Okay, and then this one is going to be measuring common phi. Is this right or not right? So if you can hear me, I want you to tell me, is this correct or not correct? You can put on your microphone. Joshua, is
Yes,
this
sir.
correct? Is this labeling correct? If the fly direction is in this direction, will this bubble truly measure common phi? Okay,
Um,
or not? Is this right or wrong? Fly direction. Is this right or
it's
wrong? This
right,
I'm saying that common omega is this bubble, common phi is this bubble. Is it right or wrong?
right.
Okay, thank God you got it wrong, because you are not had it wrong, I would have known. Like, you don't understand. No, I'm just kidding. I'm kidding. You see, if you want to rotate something about this line here, this fly direction, okay, if this direction is the fly direction, we are saying that the fly direction in photogrammetry is the x-axis. And we've
Yes, sir.
also agreed that rotation about the x-axis is known as, so x is omega, and then y is phi. Okay, and we said that during absolute orientation, then we cannot talk about common omega. So common omega is only used when we are dealing with the model. You need to understand this, otherwise you just be making mistakes. I think once you understand, you don't have to chew anything. But basically, so the rotation about the x is omega. Are you okay? And you can see clearly that the reason why this is wrong is that, come in, let me get this. The reason why this is wrong is that if I want to measure how something is rotating, if the airplane is moving in this direction, then it means the wings are where? The wings are here and here. So if the wings are here and here, then the rotation about this, you can look at the bubble itself. If the bubble shifts down this way, it means we are going in what direction? If the bubble goes down like this, it means the whole thing is, tilting about in the top and down. Are you get what I'm saying? This bubble will not be able to tell you if we start tilting in the y direction. This bubble will not be able to do that. This one will do a good job. But this bubble is very good when we start having a tilt, what we call a pitch. When we start turning, the airplane starts diving down or diving up. Are you okay? So
Yes,
think
sir.
about the airplane, think about the model. Think about the airplane, think about the model. Are you okay? Because obviously the orientation of the airplane is almost the same as, that's why we are trying to have the vertical photography. It's the same as what we have in the model. The model is only two exposure stations represented by projectors. Okay, the model is only a representation of reality. The reality is that an airplane flew and then took, shots, captured certain views. All right, so this is one, this is supposed to be common omega, and this is supposed to be common phi, because this is about y. This measures about y. So if I were to draw a line to show this is why this is wrong, I'll just do this, and then I'll do this, okay? And then this is x, okay? So this is x, and then this is the x axis, okay? And this is the y axis. And so easy, y is phi, x is omega. So making this wrong. Are you okay? All right. So I think we need to understand like some of the terminologies and how this is achieved. If you have any question, you can ask though, but I'm not in a hurry to go. Yeah. So, but this is the idea of using the inclinometers. You remove the inclinometer when you set up the first model. You make sure that they have been placed at the center of this one. Yeah, these bubbles are at the center of this one, reading 0. And then so omega will be, delta omega will be 0, delta common omega will be 0, delta common phi will be 0. And then when you introduce the next photograph, you make sure that you have, done arrow and AO. And when you do it, and you make sure that these bubbles have come back to the center of the run. If that happens, it means now the first model you form and the second one are in the same, orientation. The whole idea making use of these analog methods was to now, measure from the model. Are you okay? So you'll be actually mapping the ground from the model and then introducing more diapositives, and you keep on mapping. Are you okay? But at the end of the day, what you wanted to extract is a map from the model. So once it is done, it's done. It's not good. But then with digital systems, you could always, anytime you want to access the model, if it's a elevation model, surface model, you could always measure it. These are all techniques, but a student is supposed to understand them. Like I said, for obvious reasons, maybe they may become a professor. Are you okay? All right. So that is it for you. So I don't know where we will talk about what I just talked about, but yep, it's in there somewhere when you read it. Are you okay? So we make use of sensitive spirit bubbles. Remember, I'm talking about spirit level. When I say spirit level, spirit bubbles held at right angles to each other. I think I've talked about that already, right? The inclinometer is placed on the right hand plate. Good. The two bubbles are then leveled up using finely. Again, that if they are leveled, it means you bring them to the center of each one. Okay, that's what it means. Then you take them out. Like I said, the next model is set up. That's what I said to you. So you can read about this, okay? And then yeah, it should be just fine. The last method really is in between analog and then digital. So we describe it as the semi-analog method using independent models. Is that okay? Semi-analog. So it's not fully analog. Is that okay? But then basically what that means is that we carry on with some of the things we've talked about in terms of relative orientation, all that is done. But then in joining the models, it's a mathematical process. So you make use of orientation and shifts. Remember, we just talked about the similarity transformation, conformal transformation. So OI plus 1 is exposure station I plus 1. Okay, so more or less O for perspective center. Okay, and then obviously with this prism that we have actually drawn represents the model. Are you okay? All right, so from the perspective center to the model itself. All right, a few things that are happening here is that an equation is applied which makes use of a bulk shift. Remember, we talked about transformation. Transformation is so it's assumed we are moving from one coordinate system to the other as we transition from the first model to the second model. So there's a bulk shift, there's a scaling, and there's a rotation, as we've talked about already. All right. So rotation matrix is applied. Is that okay? So pictorially, this one means to join two modules, bi plus 1 and then bi plus 1 prime may not coincide. Is that okay? I'm actually talking about this and this. They are supposed to be at the same place. All right. but they may not be. It's all right. So our job then is to use the transformation process to bring these two so that they coincide. It's all right. And what a simple job we have. Just apply formulas. Is okay. The shift, the rotation, and the scaling. And there we go. So we have this equation here. So the shift is this bit. That's the rotation. That's the scaling lambda. Okay. And then we get the new set of coordinates for the transformed one. So you can really, if you understood the coordinate transformation, you can apply it to what we have here. Except that the rotation matrix R is not as simple as you are seeing here. It's a rotation matrix. It's not just one value. Are you okay? Even though in our example, rotation was, we use the trigonometric functions to represent the rotation, to effect it, the rotation in the transformation from the unknown to the known. Are you okay? All right. So that is that for Ariel triangulation, which is no different from some of the things that we actually trying to do in photogrammetry. The ultimate is to bring all the photographs together. What we are doing in Ariel triangulation is to bring all the photographs to join them up, All right. So this page is dedicated to explaining it. I think it's just a generous way of revisiting some of the things that we already know. Are you okay? So we're talking about what is a strip of photos. Area photographs acquired from mapping are taken at regular intervals along a straight flight path to form a strip photos. I think so. If you're not sure, I'll be mentioning strip and all those things. This page is there to help you. Are you okay? And to put in perspective, what we are trying to achieve in photogrammetry is to have what we call photographic coverage. Is that okay? All right. So forward lap, I think we've learned about it. Okay. Overlap region, I think this is being talked about, 60% overlap. It's very important as we do coverage. Let me tell you where we are heading towards. We are actually heading towards, the bundle block adjustment. So this is a nice way of, just like an aeroplane that's trying to land. So these we are revisiting some of these stuff. We can have the triple overlap, like I said. You can have the first common overlap, but you can introduce a third photograph because of what we did with the Ariel triangulation. That common, that N2 prime, N2, those points, which are necessary in joining the model. So we don't only want to have a model, we want to have models that can be joined in such a way that there's a seamless, continuum. They are together. Are you okay? All right. So we are revisiting some of the things. Triple overlap. The side lap is the airplane going on one direction and then coming back. All right. And then they will now having two strips overlapping on the side. I think we have to remember these things from photogrammetry 1. So this is a generous way of reminding us. All right. Now there's what we call tie points. Okay. So points in the side lap selected for joining neighboring strips are called tie points. Remember this is okay. So the side lap, we need something, which means that models don't only need to join to form a strip model. We need to also have a block model made up of joined strip models. Are you okay? So if I'm asking you questions as a student, is your understanding of what I'm talking about that I want to know. If it's an online exam, take-home exam, you need to really understand these things. Otherwise, you'll be writing wrong stuff. That don't make sense. All right. So models assembled into a strip or block of spatial models can be regarded as single model. Are you okay? Concerning ground control requirements, blah, blah, blah. Okay, so this is a very nice refresher, something for us here. Okay, pictorially, this is what is happening. Plane goes that way, pictures are taken. Are you okay? We have an overlap, forward overlaps. Are you okay? Then we have the side lap. So this is a side lap or lateral overlap. It depends on whether you're an American, Canadian, or British. So some of these words, You know, when you are saying side lap, someone is also saying something else. Okay. All right. I want you to also know what a pass point is. A pass point is a photo control point developed and used in the analytical triangulation process that ties adjacent photographs together. Okay, so take note of the pass points. Is that okay? All right. So yeah, and so on, blah 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 blah. I think most of these things are already talked about. Yeah. ST orientation, I think I've seen already ST orientation here. We talked about interior orientation, relative orientation, and we talked about absolute orientation. But exterior orientation really is just determining the GPS coordinate, XYZ coordinate of where the camera is. Okay, when the exposure is being taken, and also omega, phi, and kappa. Okay, so you can denote exterior orientation by the following parameters. You can just say x naught, y naught, z naught, comma. So all these, then you can have omega naught, phi naught, then kappa naught. Okay, so there are 6 values that you need to define the so-called there you go again, exterior orientation. Okay, so writing with my mouse is difficult and Microsoft Whiteboard has not been nice to me. All right, I wish I could just write, but it doesn't work. All right, so let me just leave it there. So there we go. Let's go back to our notes. All right, so I'm touching a whole lot that are supposed to put things in perspective. Are you okay? While we are doing what we are doing. So I keep saying that photogrammetry is a simple story of someone trying to find out how they can measure an area without going to the ground. But then he has to go to the ground a few times. Okay. Growing up, we used to say that white people are very lazy. Of course, they came out with some of these theories. Well, somehow challenge me. A Pan-Africanist also challenge you that maybe it's a black man who came out with some of these things. So I should be careful what I say here. But obviously, that is the idea. The idea is to join up the models, okay? And as we go, there are errors that are propagated, okay? Okay, so now let's look at this diagram and see there's something we can learn from it. So the cross, the plus signs that you are seeing there are the pass points, are you okay? And then you can also see the triangles are controls, are you okay? All right, so when you see the round symbol represents the vertical control, the triangle represents the horizontal control. The plus signs are really like, you know, the so-called pass points that we talked about, okay? So they are also named, okay? And then we can look at a few things too. So here too, we're talking about a lot of models. So you guys see the triangles in this diagram, okay? So the triangles are horizontal controls, like I said, and you can have the two. Sometimes a point can be vertical and horizontal at the same time. So that is also important. So down here you have there's a key there. The tie points are represented by a round circle and then with some kind of cross in there. Is that okay? All right, let me go back to the board and see here. So we are seeing this round thing, okay? You can have a round circle with cross. So here the coordinates are actually x, y, z. I'm not supposed to write this. Why? Because in photogrammetry, capital X, Y, Z and small x, y, z aren't the same. This is ground, this is photo. So these are photo coordinates. So that is why you cannot associate, you can't write this in the photogrammetric class and say that this symbol gives you those values. Are you okay? But then it's okay to say this because this is ground control, horizontal control, vertical control. It's all right. So you can have separately vertical control, and then we can have a horizontal control as symbolized by what? Triangle, vertical control. I have the horizontal control. Okay, and then we have this as the pass points. So the pass points are like, they are made up if you really want to understand it. They are made up. Are you okay? I hope what they are showing on TV is a movie, not a real thing. Scary. Pass points. Are you okay? All right. So you can actually, like I said, you can create so many pass points on a photograph. You can have like so many of them, well spaced. Okay, so these are pass points. They're only helping us to solve for the equation. Are you okay? At the end of the day, we are trying to solve for an equation. All right. So that is that. Let's go back and look at this. So this diagram should make a lot of sense. So like I said, the tie points only exist where we are joining the strips. So this is one strip. This is the second strip. This is a third strip. And then the actual tie points will lie here where the strips are joining. Okay, so one of the things you do in photogrammetry, what we call the quantities, okay, is to just count the number of controls you have. For example, you can see that the controls are not being provided every photograph. They are being provided every third photograph. You should take note of that. So we have how many horizontal controls here? 1, 2, 3, 4. So there are 4, 5. Yes, 5 horizontal controls. How many vertical controls? 1, 2, 3. Are you getting that? So what the counting helps you to do is to establish a number of equations to write, etc. All right. So there we go. Excuse me. Yeah. So this one I use AutoCAD to draw it. It's okay. You can see the pass points. You can see the model 1, 2, model 2, 3, 3, 4, and they are all joining up nicely because there's a triple overlap. Because there's a triple overlap. So take note of that. The error propagation is such that the more modules you have added on, you have the error gets propagated the same way an open traverse also accumulates the errors as you go. And the way to go about determining the coordinates or known coordinates as you move on is to make use of polynomials, okay, and the polynomial transformation then does the actual correction for you. But then you should be careful in the use of polynomials. Okay, so here we are looking at observation, we are looking at equations. Remember, we've talked about conformal, affine, polynomial transformation. Then we can talk about least squares, which is the last one, which is the ultimate in photogrammetry. To use least squares corrections is all right. So take note of the errors. All right. Yeah, a few precautions is to just make sure that you don't over apply the polynomial that is being used. Is that okay? And also make sure that you have 1 or 2 controls as you go. Every other photo, 2 to 3 photos, you introduce a control. Otherwise, then you have a lot of errors as you go. Is all right? Okay, so use lower polynomials as well in correcting. Anytime you talk about polynomials, start thinking about solution for an unknown coordinate. Remember, that is our objective, is to find the coordinate of an unknown point. What we have in our hand are photo coordinates. Are you okay? And then what we don't know is the ground coordinates. So we're trying to solve for them. When you look at this equation up there, yeah, that is what we are trying to do. Are you okay? All right. So it brings us to the bundle adjustment or bundle block adjustment, which is like the last but one topic that we have to deal with. Is okay in this class. Try to keep it short and sweet, but it's really packed. Are you okay? Take note of that. Yeah, so The ultimate extension of the principle described in the preceding section is to adjust all photogrammetric adjustment measurements to ground control values in a single known solution. Are you okay? So forget about looking at two photographs, one single model, two models. No, all photos within the project area can be adjusted. Are you okay? So that we can compute the value for every photo point. That is the whole idea. Are you okay? Now, why do we call it bundle block adjustment? Because there are many light rays. Remember that you take a photograph. Anytime you take a photograph, you are collecting light from millions of points from the person. If you're taking a selfie, then anytime you press the button, then the light reflecting off the person or you yourself is a lot of it, a bundle. Okay, all right. So that is why we call it that. So the bundles from all photos are adjusted simultaneously so that corresponding light rays intersect at positions of path frames and control points on the ground, etc. The process is an extension of the principles of analytical photogrammetry. Obviously, once we are using equations, we call that in photogrammetry, once you are applying equations, we call that analytical photogrammetry. And in digital means that we're not even making use of any manual processes at all, just scan images. Are you okay? So which we are going to talk about. That will be the last topic, digital photogrammetry. Is okay. So in bundle block adjustment, what we're trying to do is to do what we call adjustment survey adjustment. What you've been taught? I'm sure you've been taught that topic, survey adjustments. So you are adjusting an equation. That means that you're trying to distribute the errors, correct for it. Are you okay? Somehow
Yes, sir.
redistribute. Is that okay? All right. So there you go. In bundle block adjustment, you take a set of photographs like what we see on the board, and you try to determine, the number of object points, the number of image points, are you okay, number of observations, number of unknowns. And then by doing that, you're able to now establish the number of equations that you'll be solving for. Okay. And then you go ahead and then you plug it into software that does the actual adjustment for you. So most of the time by using the software, you don't have to worry about some of this. But what you need to know as an engineer is to know like the number of equations to put in there, where to place your controls, where not to place them, because otherwise your solution will come out with a lot of errors. Are you okay? All right. So here we are saying we have 26 object points. So let's go to the diagram. See, so I don't know if you are following it. Can you determine why we have 26 object points in this diagram? 26 object points. Why do we have 26 object points? So this is why we have 26 object points. We have 20 pass points, okay, which really we can identify on the ground. 1, 2, 3, 4, 5, 6, 7. You go all the way to 20. Then we have 6 control points. So we have A, B, C. These are actually X, Y, Z, okay, horizontal and vertical control points. A, B, C, D, E, F. That's 6. Is that okay? So that gives us, for starters, 26 object points. Are you okay? All right. So that's one of the things that we do in this area of bundle block adjustments. Are you okay? We do that. It's like the quantities of photogrammetry. All right. Also, we have 76 point images. So how do we come by this? So you have to separate the photographs to be able to determine that. Separate them up. So as you're looking at over here, we've separated it into the various components. So in the block, we have overlaps, which are not easily seen. We can't easily tell, but we can separate it up. This is one photo. That's another one. Are you okay? and then we introduce a third one, and the final one. So you see, it gets quite complicated, but then how many have I drawn? I've drawn 4. Are you okay? So moving downwards, we can now separate it into 4 on top, 4 below. All right, so that's what we have over here. So here, these points are actually, this area is the overlap region. Okay, so you can see 1 is here, A is here, 6, 7 is repeated. Okay, the perspective center is actually the box with the cross in the middle of it. It's the middle of the center of the photograph, more or less. Now you can see that we have the center of the second photograph also appearing. So if this is, the first one, all right, so you can see that the second photograph is here, third one, and the fourth. Are you okay? So model 1, 2 is when we shift these two together, and then we now have a common overlap region. Is that okay? So now, what are we trying to really achieve? How do we get 76 point images? So when we take photo 1, okay, you can see that photo 1 looks similar to photo 4. Okay, so this becomes the 5th photograph. This is the 6th, 7th, and the 8th. Okay, so 1, 4, 5, and 8, they all have 2 controls and then 9 pass points. Are you okay? 2 controls and then 9 pass points. That gives you a 11 point image. So 11 times 4. So if you go back up in the diagram, then we can see the reason why we are having that calculation. Sorry, this has to go with it. So the 4 times 11 that we are seeing here, okay, things are shifting a bit, but yes, I just wanted you to see the 11, but 11 is covered by this red line here. Okay, so let me just clean that up. We're getting 4 times 11. This is the reason. Are you okay? We separated the corner photos. The center photos also look similar. So the photos here in the middle, they look similar. So for them, we have 9 plus, how many controls are we seeing here? Plus A and then B, obviously. Yeah, so here 6. The corner photos are going to be like 6, obviously plus 2. And then this one's going to be 11. Are you okay? All right, so 4 times 11, 6, 8 times 11. Are you okay? Corner photos are 6 times 11. Are you okay? So that is how come we're coming out with this equation. 8 is actually the 6 photo images. Are you okay? The 6 pass points plus 2 controls. That gives us 8. 2 controls plus 9 photo images for the center image photos. Are you okay? Now we get 76 point images. What it means is that point images are not really on the ground. It's just one object, but on the photos they are appearing so many times. So we have more of it. That's why we're having so many of them. The unknown quantities to be obtained in a bundle block adjustment consist of 1, the XYZ object space coordinates of all object points. Is that okay? Remember how many object points we have? 26. So it's trying to tell you the number of unknowns, total number. It's going to be a very huge value. The second one is the exterior orientation parameters. I've already talked about this. Remember, I talked about the exterior orientation parameters not too long ago. The first group of unknowns, objects, is necessarily a result of Ariel triangulation, blah, blah, blah. But anyway, I don't have time to read all that. So it makes sense that the unknown quantities, are you okay, in terms of number of unknown object points is 78, okay, plus the exterior orientation the stereo orientation, how do you obtain the stereo orientation parameters? Joshua, how do you obtain, why do we get 48 for stereo orientation parameters?
8 by 6.
8 by 6. And why 8? Why 6? What are the stereo orientation parameters? When the plane is flying, just say it that way so that it makes, when the plane is flying, exactly how are we able to talk about stereo orientation? What orientation is that? How does it work? You know interior orientation, right?
Come again.
You know interior orientation. Let me correct for atmospheric correction, lens distortion. Are you okay? The centering the photograph. And relative orientation is where we are correcting for the Y parallax. Are you okay? Then absolute orientation is where we are leveling and scaling the model. Are you okay? In exterior orientation, we are determining the coordinate of the perspective center. In other words, we want to find out the position of the camera at the point of exposure. Are you okay? At the time of exposure. And so, how come we are getting 8 times 6? So we are getting 8 times 6 because if you actually look at this diagram here, we have how many exposures? 1, 2, 3, 4, 5, 6, 7, 8. And each one of them has omega phi kappa x, y, z. Are you okay?
Yes, sir.
That's why we have 8 times 6. Okay, great. Well done for answering it right. Just that let the justification wasn't coming. Anyway, so when we add them up, we get 126 unknowns. 126 unknowns for just 8 photographs. So we have 126 unknowns. So you can imagine that the kind of equations that we're solving in JHS, primary, whatever, SHS, simultaneous equations, how many unknowns were there? 2. And yet people were struggling to solve it, isn't it? How many unknowns are we looking at here? 200 and what? 26. So yep. And what equation are we talking about? We are actually talking about the equation. So in fact, we are going to talk about the equations which we are solving for very soon. They are called the collinearity equations. We talk about them very soon in analytical photogrammetry. All right, great. What are the measurements? We make measurements on the photos. In other words, we measure the photo coordinates. The second one is that we observe SY coordinates of the ground point. Remember that in photogrammetry, you can't do without the ground coordinates. So these are also observations that were made, observed quantities. The third one is a direct observation of the exterior orientation parameters. So now the exterior orientation parameters, we can choose to add them or not. That's one thing we should put in our mind. So when we add them all up, the total number of observations will be 152 plus 18 plus 40. So 48 is definitely the stereo orientation parameters, which we just calculated. And then the 18 is the ground controls, which we have. We have 6 of them. Remember, 6 times every control on the ground, which has horizontal and vertical values, will have X, Y, Z, which is 3. So 3 times A, B, C, D, E, F, 6 times 3 will give it 18. So 18 plus 48 plus 152, which are the photo coordinate observations. Are you okay? So we are having 218 observations. Now remember that we learned something in the similarity transformation, and we said that given one control, we can write how many equations? Can write 2, isn't it? So the number of observations to solve for, let's just take similarity or what you call it, simultaneous equation. 2 unknowns, how many equations were needed to solve it? 2, right? Okay, so it means that if you have 126 unknowns, how many were 226 unknowns up here? Then
So
we need a minimum of 120 six
Six.
equations to solve it. Are you okay? Okay.
Yes, sir.
So in fact, in the exam, the questions I ask about is, I'll just put 3 or 4 photographs there and I'll ask you how many equations. I'll just ask you, and people be writing all sort of things. Someone writes 0, someone writes 2. It's kind of interesting. It's your understanding of what is the unknown, what is known, what is being measured, etc. All right, so that is bundle block adjustment. The rest is software. Let me not worry you about going to solve some big, matrix on your own on a sheet of paper. Software will do it for you. But for you as an engineer, you need to understand, even when a software is solving something, you need to be on top of it and say that this value shouldn't be like this. This is too small. This is too large. This is the number of equations. These are things, that you need to know to carry on. So this is it with our bundle block adjustments. I think the Zoom is giving us some free time, isn't it? Should have cut by now, I'm thinking. When did I start this lecture? 4:30. What time is it? 5:45. So we've done an hour.
Yes, sir.
Okay, so Joshua, I think we're going to end it here. Is that okay?
Okay, sir.
And we'll continue